I will come to Hertzian dipole, actual Hertzian dipole. Up to now, we build up or we have built up the foundation for Hertzian dipole. From now onward, we'll go to Hertzian dipole. I will start that with a salutation to important scientists or whom I hold in very high regard. I held all scientists in high regard, but these are people who have made changes or who have made changes in our life which are profound in nature. First one is Sir Isaac Newton. Then the next one is called James Clerk Maxwell. From Maxwell, many people were inspired. One of them was Heinrich Hertz, and other one is Albert Einstein. These two people. So you remember, you know all these three: Newton, Maxwell, and Einstein. Their contribution to physics is unparalleled, and they had impressed or their impression or influence over the society, over science and technology in those days is profound. Nobody else has that influence. The influence these three people had, nobody else had that influence across all fields. So therefore, I salute them. Then Maxwell had inspired many people. One of them is called Heinrich Hertz. What Maxwell did is, for us, for people in electromagnetics, Maxwell worked across the physics. He worked in heat, he worked in electricity magnetism. In electricity magnetism, he found out two things. One is light is a form of electromagnetic wave, and light travels at the speed of 3 into 10 to the power 8 meter per second. These are two things beyond the unification of electric field and magnetic field. But Maxwell was not very strong in vector calculus. So Maxwell gave us 20 equations. The equations that you read today as Maxwell's equations were not proposed by Maxwell. But people were inspired by Maxwell. One of them was Heinrich Hertz. Heinrich Hertz has put those 20 equations in a compact form of the 4 equations that we read today. And out of his respect for Maxwell, he called those equations as Maxwell's equations. So the equations that we read as Maxwell's equations were not proposed by Maxwell. These vector equations, they were by Heinrich Hertz. Maybe sometimes else we can discuss on this. We can have a complete discussion on this. But Heinrich Hertz made another thing. He designed the first antenna without knowing that it is an antenna. In his quest for verifying whatever has Maxwell told are correct, he designed the first antenna. I will discuss that later. After Heinrich Hertz, around the same time, Sir J.C. Bose also designed an antenna without knowing it as an antenna. But he also designed an antenna. But these two gentlemen, what they did is, they found that there is actually electromagnetic wave which is existing and which can be felt at a distance. You generate it at one point, its effect can be felt at a distance. Both these persons, both these gentlemen, great scientists, one is from Germany, other is from India, they did this. Then came somebody called in the name of Marconi. You all know Marconi is the inventor of antenna. Anybody who is into electromagnetics or electronics or a general knowledge is Marconi is the inventor of antenna, which actually is not a fact. The fact is Henrik Hertz and J.C. Bose. Of course, Henrik Hertz was rudimentary. J.C. Bose was much more profound, much more focused, but they failed to use their instruments for communication. Marconi gets the credit for communication using his transatlantic experiment. This is his transatlantic house, from which he transmitted electromagnetic waves or fast telegraphic transmission, wireless transmission across the Atlantic from Europe to America. So that is what is the credit of Marconi, for which he got the Nobel Prize. But remember one thing, that he is not the person who invented antenna or who designed antenna. That credit should go to Sir J.C. Bose, although he was not able to use it for communication like Marconi. In other words, J.C. Bose was out and out a scientist. Marconi knew how to convert scientific knowledge into profitable business. So Marconi became a scientist businessman. J.C. Bose remained a scientist only. Same thing is with Hertz. But for Hertz, we'll discuss in the next slide. So, what Hertz did is he conducted one experiment. In 1887, he had his apparatus. So left hand side is Henrik Hertz. You can see his lifespan is hardly 47 years. Right. He and Maxwell both died in their 40s because of cancer. Maxwell because of stomach cancer, Hertz because of a cancer in the root of his teeth. So both these people, we lost them at early age. We could have got many more things from them if they would have lived. But nature is nature, it took them away early. So this is one apparatus that he designed, Henrik Hertz designed in 87 for generating and detecting radio waves. Radio waves or electromagnetic waves were proposed by Maxwell. Maxwell said that they exist, but he could not show that they exist. Maxwell proved theoretically, experimentally, he could not show it. Right? So what this apparatus does is, it generates a spark in the gap between two dipoles. Look at the figure. What is there? It consists of a dipole antenna with a spark gap. S is the spark gap in the schematic. Look at the schematic. S is the spark gap. In that spark gap, we generate a spark, high voltage, right? So that is generated using 50 Hertz, and he received it using a loop type of receiver. Right? Once he received it using a loop type of receiver, what happened actually is, he generated a spark in the spark gap, and he had a receiver loop. In the loop also he got a spark after a finite duration of time, small duration of time. Right? From that he concluded that actually electromagnetic waves exist. We cannot see the electromagnetic waves, but they exist. And they travel at a speed which is the speed of light. He just calculated what is the time delay, what is the distance between them. From that he calculated the speed of light, and it matched to that proposed by Maxwell. So finally he said that, I quote Henrik Hertz, "It is of no use whatsoever This is just an experiment that proves Master Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there. After the experiment, this was his conclusion. Somebody asked him, what will be the application of this discovery? Electromagnetic wave you have discovered, what will be the application? Her reply was, I quote, nothing, I guess, which means he was unaware of the enormity of his discovery. You know, today we know what it means. Electromagnetic waves, their propagation, etc. We know what it means. Right? So this is the dipole that he used for his experiment, and in respect to Heinrich Hertz, the elementary dipole that we are considering is called Hertzian dipole. The dipole that we will consider now, from now onward, is not the dipole that was experimented by Hertz. We will consider the dipole that exists within a material medium or because of a source. So we'll now move to Hertzian dipole. For that, we'll make certain assumptions. The first assumption is it's a point dipole. So it has no extension, it is like a point. Second is it is located at the origin at dash is equal to 0. Third is it is oriented along Z. So if it has any extension, it is along Z axis only, not along X, not along Y. So its orientation is along Z. Fourth is, which is most important here, it is time harmonic in nature. Fifth is, it has dipole moment P, which corresponds to its polarization, material polarization in which it exists. So it is corresponding polarization, which means dipole moment per unit volume, PR is equal to small p delta cube R. What does that mean? It exists only at the origin, nowhere else. At other places, it does not exist. It is 0 everywhere else. Now, we will find out what will be the polarization current and charge density. So J pole, we have found out an expression for this. Polarization current is dou P by dou T. Similarly, polarization for charge is equal to rho divergence of P e to the power j omega t. Now, how does we get this? For P, we write P into e to the power j omega t or P into exponential j omega t. Take time derivative, so j omega P exponential e to the power j omega t. Rho pole, similarly, for P, we are writing e to the power j omega t. Since we are considering time harmonic fields, and therefore, in our development, in all our equations further, there will be no time derivative, no time. So no time, so we'll exclude these e to the power j omega t terms. So excluding that, we'll consider only the spatial part. So j r will be equal to j omega p, and rho r will be equal to minus p dot del grad of del cube r. Why it is so? Why it is minus p dot del? In the above line, first line we are saying del dot p. In the second line, we are saying rho is equal to minus p dot del. Remember one thing, this del is not only a vector, it is also an operator, right? Since del is an operator, it is operating on R. What is P? P is dipole moment. Dipole moment is independent upon R. Therefore, but it is a vector. So we take del is not operating on P. A dot B is equal to B dot A. Therefore, we interchange them. So P dot del is operating on R. So del cube R. So that is how we get rho R is equal to minus P dot del or grad of del cube R or del R. Now I will call it impulse of R or impulse R instead of saying del Q from now onward. Now, once we know what is J, what is rho, we can find out the potential. So what will the potential? We have vector potential, we have scalar potential. Vector potential will be equal to mu 0 J R dash G R minus R dash and integrated over a volume. This we have already seen up to now. So put for J R dash J omega P d cube R. So mu 0 is constant, take it outside the integration. Inside integration J omega P, then impulse, then G R minus R dash d cube R. You know that integration of fx delta x minus x0 over the volume gives you f of x0. Use that property of delta. So you get J omega mu 0, those are constants, they remain as it is. Gr impulse of R dash over volume, that gives us G of R. So AR is equal to J omega mu 0 P into G of R. So that is my vector potential. What will be the scalar potential? Phi R will be equal to 1 upon epsilon 0 integration rho R dash G R minus R dash over volume. So this comes from again from convolution of charge with Green function. Now for the charge, I will use P dot grad of the impulse function. Then we'll take the convolution of that with Green's function, and convolution is over the complete volume. So that will give me, once we do the convolution, that will give me 1 upon epsilon 0 P dot grad of GR. So we will get this grad of GR, and that is equal to delta dot A upon J omega mu 0 epsilon 0. How do I get that? I remember the Lorentz condition. So if I use the Lorentz condition, phi R using Lorentz condition is equal to divergence of A upon J omega mu 0 epsilon 0. So now we have got the solutions for both the potentials if we are considering a Hertzian dipole. The field for the Hertzian dipole, the fields will be, I will use K is equal to omega upon C or omega root over of mu 0 epsilon 0. This, without saying, this goes with us everywhere, wherever we are dealing with K, omega, mu epsilon, this relationship goes with us. Now what is H? 1 upon mu 0 curl of A. We have found out what is A. Put that 1 upon mu 0 curl of J omega mu 0 P and GR. Now curl is not operating on P, so take the P outside. Mu 0 cancels out. What we are left out is J omega P cross product with gradient of G. Similarly, for E, it is 1 by epsilon 0 gradient of P dot del plus K square P operating on G. Now I will leave this as a classwork for today. For you, do this classwork. The hint for this classwork is E is equal to 1 upon J omega mu epsilon into grad of divergence of A plus K square A. Use this